And so we had 5 talks and 1 workshop. So those who are interested in reviewing or want to see the recordings, all the recordings are available on our YouTube channel. We will share the link in the chat window in a while, inshallah, in the workshop. Now I'll stop sharing my screen. Oh, you can, yeah, you can see the screen now. These are the previous speakers. So far, they have conducted talks in our monthly seminar series. I don't know if you can see my screen or not, but it seems now it's fine. You can see my screen. So they were the speakers. So just a few housekeeping rules before I introduce the distinguished guest speaker, Professor Awais. We have muted all participants, and please do keep yourself muted unless otherwise stated, asked to do so. So also please don't turn on your camera unless advised to do so. The format of this talk would be first 40-45 minutes for the presentation from Professor Awais Rashid, followed by a Q&A session for 10 to 15 minutes. You can type your questions in the chat window. During the Q&A session, I will read out your questions to the speaker. At the end, we would love to know your feedback about the seminars. We would like to improve our seminar series, so we need your assistance. We will provide you a link in chat window at the end of this talk for this purpose. Now, let me introduce Professor Awais Rashid. Professor Awais Rashid is a full professor of cybersecurity and at University of Bristol, UK, where he heads the Cybersecurity Research Group. He is the director of EPSRC Center for Doctoral Training in Trust, Identity, Privacy, and Security in large-scale infrastructures. He is also the director of National Research Center on Privacy, Harm Reduction, and Adversarial Influence Online. He is also editor-in-chief and principal investigator for the cybersecurity body of knowledge. His research interests are in the security of cyber physical systems, software security, and human factors. He leads projects as part of the UK Research Institute on Trustworthy Interconnected Cyber Physical Systems, UK Research Institute on Socio-Technical Cyber Security, the Digital Security by Design Hub Plus, and the Petraeus National Center for Excellence in Cyber Security for IoT. With this, I will ask you please to join me and help me in joining Professor Awais Rashid. So now, Professor Awais Rashid, you may join and you can please start when you are ready. Thank you very much.
Okay, thank you very much, everyone. And my apologies, I had some challenges this morning with getting this to just joining the webinar. And after playing around with various authentication problems, I'm here. Thank you for waiting. I'll start. So if I can share my, will you please give me rights to share my screen? Thank you.
Yes, please. Just hold on. Okay, now I think now.
Yeah, I can. Thank you. Okay. So I hope this is visible now. Okay. Well, thanks again, everyone, and apologies for the complications at the start. My thanks to the Saudi Aramco chair and Professor Nasser Manila as well for inviting me to give this talk. I'm Awais Rashid. I am Professor of Cybersecurity at the University of Bristol, where I also am director of our Center for Doctoral Training in Cybersecurity, and I also head the National Research Center on Privacy, Harm Reduction, and Adversarial Influence Online. Today, I'm going to talk about cybersecurity of industrial control systems. I will go into some of the challenges and research directions in this area. Before I go into the talk, I want to just give you a short background of what we do in our research group here at Bristol. our focus is very much on security and privacy of large connected infrastructures. So the kind of things that bring water, power into our homes, manufacturing environments, smart building environments. We've also started to look into agricultural technologies in this regard. And we do also work on things like the internet backbone. So as a result, a large part of our work tends to be on cyber physical systems, but we also look in a lot of detail at software systems. And we are an interdisciplinary group, so we also look at human factors in this regard. And of course, how adversaries behave. So, understanding attacks so that we can mitigate the impacts through suitable defenses. We are involved in a large number of different programs of research, some major national centers such as Petrus, which focuses on IoT, and RITIX on cyber physical systems. We also run a state-of-the-art testbed, which I'll come to in a moment. And we are involved in various other programs that are listed here. One I wanted to flag, if there are students in the room, is CyBOK, which is the Cybersecurity Body of Knowledge. It is a resource that has been developed by a large number of international researchers and practitioners, over 110. To provide foundations for cybersecurity as a discipline, and it's freely available. So you're welcome to go and use it. And it has a number of really interesting fundamentals that you can learn about all sorts of different areas in cybersecurity. Before I go into my talk, I would also say that this is not my sole work. We are a large team, so this is collaborative work with others within the group and beyond. Some of the materials do come from CyBOK, and some images are from news sites such as BBC News. So why cybersecurity of industrial control systems? This is something that has been in the news recently quite a lot. You would have seen not long ago, a couple of years ago, the Triton attack on an energy plant in the Middle East, where malware actually impacted the safety system of the plant in the first instance. The Ukrainian power grid attack has been in the news for quite a long time, but very recently, we also saw the impact on the Colonial Pipeline within the US, where ransomware attack basically brought the whole infrastructure to a halt, and the US had to pass emergency legislation for fuel supplies to continue. And also the last one here, where a hacker could interfere with the integrity of the water supply, the treatment of the water supply in a Florida water utility. And in fact, this was spotted by a human who observed that something was going wrong, a human operator in the plant. So the question that naturally begs itself is, why are we seeing increasing number of these attacks in itself, and where actually are the vulnerabilities in these kind of systems? Now, the vulnerabilities come from the fact that traditionally most of these systems tended to be critical infrastructure, so they were behind walls and barbed wire, and they were traditionally air gapped, so they weren't connected to anything on the main internet. But that is no longer the case. As we've got increasing connectivity of devices, it's much more easier and practical and cost effective that we can actually get remote telemetry from these systems. We can monitor them real time. We can identify where problems are happening. We can manage production much more efficiently as a result. And we want to connect them to, for example, back office systems where we can do all sorts of analytics. There is increasing use also of cloud technologies, especially as IoT or industrial IoT becomes more mainstream. So these systems are connected to the internet. They were traditionally very proprietary technology. And anybody who works with these systems know that they use their own specific types of protocols, specific types of architectures, and they were not very widely understood, but that's no longer the case. Also, like most of the legacy environments, these systems were not designed with security in mind. They were meant for real-time properties, because you want to be able to operate your process under particular time considerations. They were meant for safety. So the device designs often tend to be quite simple, because you want to be able to prove certain safety properties about them. So as a result, when these systems have been started to be connected to other systems, security has been more of a retrofit rather than a core design consideration, and it plays a secondary role to safety, reliability, and availability, which are paramount properties. However, it also creates a double-edged sword in the sense that if you've got security as a secondary property, but you can compromise the security of the system, then you can impact those very safety, reliability, and availability properties that you hold dear in the first instance. The other problem is that the network stacks in these systems are poorly implemented. So most of the protocols that exist and have been used for a long time are vulnerable. They have no authentication built into them. Often, plain text communication, as well as various other problems. Okay, and as I mentioned, these systems are not something that we buy a phone and we change it after 3 years. The devices and software exist over decades, and often old systems are mixed with new. So, for example, if you are going to actually go and update your whole infrastructure with some of the latest and greatest, say, controllers from Siemens or other providers, it's not a case of just sort of changing one. You have to have a huge infrastructure upgrade program which can run into hundreds of millions in the first instance. So what are the potential various pathways to attack? So if you're not familiar with this figure, this is known as the Purdue architecture, where at the bottom is the safety zone where there are safety critical devices. But what's in the middle, you've got the manufacturing zone, which is typically what you would call your industrial environment. You've got your processes, your basic controls, your area supervisory controls, and your SCADA systems. And then you've got your enterprise network. Now, this presents a very neat, clean-cut picture, but the reality is that there are many connections increasingly across these layers. So how do you actually compromise these systems? The simplest way is going through the enterprise environment, which is what we saw potentially in things like the Colonial Pipeline, where a ransomware attack actually brought the system to a halt. And how do you do that? I mean, these are your standard attacks that you see in IT systems. So you've got things like drive-by attacks. You can do spear phishing. You can send weaponized emails. There may be application vulnerabilities or misconfigurations in that environment. But you can also directly compromise systems in the manufacturing zone. So there are systems such as data historians that exist. These are effectively software platforms. You've got SCADA platforms. You may have engineering workstations, and you may have internet accessible devices. So if you're not familiar, you may want to go and have a look at Shodan in a responsible way. So you can search on Shodan and you can see if there are control systems that are accessible on the internet, and you can see what kind of information can you access about them. In some cases, you just end up with a login page. In other cases, you may have much more significant access to these systems. And I'll come to one example shortly. But there are other complexities. You have very complex supply chains. Okay, so you are procuring these devices, but they are being built in many different places, and those components are being taken from many different places. You may have a number of different software and service providers in your environment. You have external remote services, because driving down 3 hours to a remote facility to fix something or to monitor something is infeasible. And as I mentioned, you've got vulnerable protocols here because everything often tends to be in clear text and non-authenticated and no encryption. So what do we see as a problem? I'm going to use an example from a piece of work that Simon Foley did a few years ago, where he actually looked at what happened in configuring such a system in a real world environment. So Simon did a search on Shodan, and he found industrial system in Ireland that was connected, that he could find on Shodan, and he saw that there were various issues with this system. So the thing that he noted was that port 102 was accessible on the internet. This is part of the Siemens S7 protocol that is used by a lot of Siemens devices. He wasn't sure if this one was an unintended configuration or a misinterpretation of guidance from Siemens, because the Siemens manual noted that if you transfer the data over routers or if firewalls are used, the port must be enabled. Okay, but it also recommends that port 102 is blocked by default in routers and firewalls and must be enabled for the complete transfer route. Okay, now this device had a Siemens S7300 CPU, which was running a version of one firmware which had hard-coded user ID and password. It also has a CV on which indicates that it's vulnerable to denial of service. Now, as a responsible researcher, Simon didn't do anything with this information, but he decided to actually report and see what happens. So in 2016, in March 2016, and he watched this over a year as to what happened. So he got in touch with who was likely the director of IT by email and highlighted the problem, and also offered a proposed solution, which was based on the UK Centre for Protection of National Infrastructure guidance. The email was acknowledged. Okay. And he did not take further action himself, but he monitored Shodan for a year to see what happens. So shortly after the configuration, after he notified them, the configuration changed with the addition of a Microsoft Remote Desk protocol on a different port, 3389, but port 102 remained open. In May, all the systems and services disappeared from Shodan, and this might indicate that the system was successfully configured and the VPN access was concealed. In June, it came back again. This time, not only port 102 was open, port 3389, the remote desktop was open, and also port 7547 was open as well. In October, port 102 was closed, but 3389 remained discoverable, displaying a Windows login with a specific user ID and prompting for a password. Potentially, you could think of brute force attacks. In December, the system and all its services again disappeared from Shodan, which implied that it had been configured correctly. But in March, it was back again, and this time with port 2000 discoverable with a remote anywhere login prompt that was available over HTTPS. Okay, so the thing that we take away from this is that people do want to connect these systems to other systems because they need to be accessible, but often the implications of that connectivity aren't clear, but also how do you configure and what you configure to get the service that you want without impacting security is a hard task, because in most of the cases, people who use these systems are not security experts. So what kind of attacks are possible in these kind of systems? So this is a very simple control system. You've got a physical process here in the middle. You've got some sensors that send some properties about the physical process. They feed those properties back to the controller. The controller uses the actuators to then impact the running of the physical process, your classical feedback loop. And you've got some supervision and configuration mechanism overseeing the controller like a SCADA system. So where are the possible attacks possible? You could attack the sensors or the actuators. For example, with regards to sensors, because sensor data can be unauthenticated, you can falsify the sensor data in itself. If it does have authentication, there may be compromised keys, but also often the remote environments tend to be far away from any any environment where there are actually personnel overseeing this, so you can actually have physical access. Okay, so most of your kind of water treatment remote pumping stations are somewhere in the middle of nowhere, and you can effectively walk up to them and have physical access. You can also do denial of service attacks on the sensors. So you can do a denial of service attack on the sensor, which means that the controller cannot any longer see what the sensor is trying to feed in, Or you can completely mask the sensor, in which case the controller operates on stale data, because the way a lot of the times these systems work is that the sensors report in on a regular channel, and only if they don't report after a while, the controller will pull them. Okay, so the controller can operate on stale data, in which case the actuator does something which the sensor might be indicating otherwise, but as an attacker, you've actually compromised the link and mask that information. You can do similar things for the actuator, because if you sit in the middle of the controller and the actuator, you can, because of unauthenticated actuator data, you can get the actuator to do whatever you want. You can also do denial of service, or you can have physical access to the actuator. You can compromise the link. So you can do man-in-the-middle attacks on any of these links. So potentially, for example, you can delay sensor data reaching the controller, you can falsify it, you can replay it, because again, there is no authentication, so you can replay the same message again and again and again, and the controller will act on that. Protocols are often open, and you can do the same from the controller to the actuator. But you can also do the same between the controller and the SCADA system. So you can delay or block the information that is going in. You can falsify. You can replay. And finally, you can actually directly tamper with the controller. So the Stuxnet attack is probably one of the most well-known attacks in this kind of setting, whereby the centrifuges in an Iranian nuclear station were spun to unsafe levels, while all the time the controller was feeding information back to the supervision system that everything was okay. And in this case, what you can do is you can actually potentially falsify the data that goes to the SCADA system. So while the controller is sending absolutely unsafe information to the physical process, you're actually telling the SCADA system and the operator that everything is okay. Now you would ask, why is this possible? Okay, so how can you do this on the controller? And the answer is actually quite simple, that you can do this kind of value tampering because of the very design of the programmable logic controllers that are here. So this is the inside of a Siemens controller, and the way things work is that you've got your raw input coming in on the left-hand side, which gets pulled into a peripheral input word. Then it is converted into a range function of 0 to 100, and this first part happens multiple times every second because it's a physical process. Things are coming in again and again and again, but then it gets into this particular variable, which is MD104. Now, this is your true value of what's happening at that particular point in time. But what the internal architecture does is it then copies it into two separate variables, okay? DB1 and DB2. One goes to the remote terminal unit and to the historian, and the other goes to the human-machine interface that is in the physical process and to the process itself. And in this case, this is configured to do it every 5 seconds. It may be every 1 hour or whatever. Depending on the nature of the process. But why is this separation there? And it is there for separation of responsibilities. It's a well-known safety property that you do not give access, write access to the processes that only need to read from a critical system, in case they end up accidentally overwriting the value that you need. So where you're actually going to have a read access, you send a separate property than where you also need read and write access. So if the RTU and the historian accidentally end up overwriting DB2, it does not impact the value of DB1, and the process operates on a true value. Okay, but this is also exactly what an attacker can exploit. Okay, so you can feed an entirely different value to the historian and to the RTU, and you can feed an entirely different value to the process and to the HMI. And before you think that this is something that is a peculiarity of a Siemens device, this is the inside of an Allen Bradley device. They look pretty much identical in the way this is done. And this is not to say that this is a fundamental problem with the architecture. The architecture is designed with safety in mind. Okay, so you do that separation of responsibility, but now when you start to look at it from an adversarial perspective and what an attacker might do, then the attacker can actually exploit that separation of responsibilities to actually carry out the value tampering attack that they are interested in carrying out. And of course, you can also directly interfere with the host or SCADA software by compromising it. You can impersonate SCADA. You can send malicious commands, and this was, used in the Ukrainian power grid attack as well. So, how do we actually study these kind of attacks? Now, one way of doing this is that you can run loads and loads of simulations, but they often do not give you a clear picture of what happens in a real industrial environment. You can go to real industrial environments, but running live security tests on a power station or a water treatment system or a fuel pipeline is not something that you can do, because any impact on these devices, which often, as I mentioned, tend to be a bit fragile because they are legacy devices and they have real-time properties, can have a real implication for large parts of society. So what we do is we actually run a test bed where we have a number of physical and virtual industrial processes and their own field sites. And we have equipment from a large number of manufacturers, whether they are software or actual manufacturers of controllers or even security systems. We use them and we can link them up in different configurations to actually do a range of security analyses on these kind of systems. So we do run, for example, a water treatment plant in the lab. There is a small manufacturing setup, and we also have a security operations center where telemetry comes in for us to do this. Okay, and we also have industrial IoT and IoT devices in itself, and various ways of linking the other infrastructures into it. But that's something that I can go into separately. What I wanted to talk about was really specifically that as we see increasing use of industrial IoT in these kind of what are called operational technology environments, then we're also seeing more and more convergence between what's happened. So here, for example, you've got your traditional industrial control systems environment here on the top. You've got your PLCs, your RTUs, and your HMIs, but you also have now industrial IoT devices, which use, for example, things like the wireless HART protocol or LoRa to interact with the system. And you may also have your regular IoT devices. You might be using smart locks, smart lighting, temperature sensors, and those kind of things. So this traditional OT environment sends its telemetry through, for example, a SCADA platform, but you also have now platforms such as Kepware, which actually aggregate data from your industrial IoT devices. And you also have cloud-based platforms, which effectively pull everything together into an analytics environment. Now, that's great if you want to look at all of this, but this convergence also creates new types of security challenges. So let's have a look at a test environment in this case. So the test environment that we set up, this was a demonstrator that we built. The test environment that we set up was that we have our traditional control systems environment. We use, in this case, the Kepware platform as a way to kind of pull data from this environment, and we are aggregating all of this into an analytics platform in the cloud, which is called ThingWorx. Okay. Now, our attack objectives are the following. Okay, we want to compromise ThingWorx. Okay, we want to create a network environment for staging the attack. We want to do reconnaissance. We want to mask our attack, and we want to manipulate the process, and we want to terminate the process if we can. So in terms of compromising ThingWorx, not particularly challenging because when we were doing this work, this platform was based on Tomcat 8.5. This is only page 1 of 2 of all the CVEs that you can find, including some critical ones in the CVE database. So compromising the ThingWorx platform, because of its reliance on Tomcat 8.5, was not a huge challenge. So once we have compromised ThingWorx, what we can do is we can start by terminating ThingWorx, okay, and we set up an HTTP listener. And again, you can say, well, why not HTTPS? We can also do this with HTTPS, but we configured this as it came out of the box, and it is set up to work on HTTP, which makes things simpler. Now, once you've done that, the engineer now can no longer see what's going on. So they think that something is wrong at their end, which is where Kepware is, and they go and open a potentially weaponized PDF, and the embedded exploit within that creates an HTTP outbound request, because ultimately what we want to create is a channel where we can run some commands and not be visible. Now, this is a particular example where we make the assumption that there is a weaponized document available. There is another way of doing it, but that's something that's not in the public domain at the moment. So we go with the simple example. Now, once you've got your HTTP session in itself, you can also set up a proxy via this HTTP session, and you've got your two-way link now established. Okay, at this point in time, you can now start to run network port scans. Okay, so you can use things like Nmap to do all kinds of things. You can also enumerate what are the programmable logic controllers that are there, and you can actually do logic code uploads to your own system, so that you can actually see what's happening in that regard. Now, one of the things to note here is that often, because of these new types of environments, you also leave now more descriptive tags on your PLCs, so you actually know much more easily as to what a particular PLC does. Now, once we have done all of that, and as I mentioned earlier, because most of the protocols in this case are open, you can do all sorts of things. So the potential attacks you can do is you can actually configure the RTU, or you can take it offline. You can freeze the HMI values on the PLC so that nothing can be done to that. You can freeze the pressure sensor values in the PLC, and you can then push the pump to run beyond safe limits. And in our actual experimentations, you can actually run the pump beyond safe limits in this regard. And if we didn't have other safety measures, because of the way we work in the lab, it would actually cause physical damage to the process. And finally, given that you are inside the system, some of the older PLCs, you can really effectively terminate the PLC quite easily. And the only way to then restart is to physically go to the PLC and turn it on and off generally. And now the problem with that is that you may think, oh, that's not a big deal. Yes, it is not a big deal if you're sitting in a lab and the PLC is in the room over there. It is quite a big deal if your PLC is in an environment that is 300 miles away. Okay, and you have to keep going to do that. But also, if you've got many PLCs in there, going and trying to find where it is and which one it is, and having to keep doing that again and again is quite challenging and costly. So these are the various issues that exist in these kind of environments. So what are the challenges? I'm going to try and wrap up now so that we have some time for questions. So one of the biggest challenges is making sense of what are the kind of known problems, and also what may be the unknown problems. Okay, and that is made harder by the fact that the understanding risk in these kind of settings, it's not just about understanding the technical problems, because people interact with these environments and engineers are used to working with them in particular ways. So it's fundamentally a socio-technical problem in that regard. But if you are trying to understand risk in these kind of environments, you've got all this, and this is a fairly, I would argue, simple lab-based environment. A realistic infrastructure will be far more complex. Okay, it will have many, many more of these systems. They will be interconnected in lots of different ways. If you're a large infrastructure organization, you run, hundreds of sites in your infrastructure, all with a large number of devices, software, hardware, and platforms. Now, if you think about it, that you have to make sense of all of this, okay, all in the presence of all this complexity, connectivity. The attacks are also increasingly on a scale that is complicated, and also the impact of those attacks and understanding. If I have an old PLC, is it going to be accessible? And what it does, is it going to have a knock-on effect on the rest of my infrastructure? Or is it that nothing is ever going to touch it, and it's okay for me to continue to run it? And understanding all of this is really, really complex. So how do you actually understand risk in this kind of complex setting is really hard, and it is made harder by the fact that we have really no good ways of measuring that. Okay, we have no good ways of measuring the security state of our industrial control systems environments. We have no good ways of measuring what are the problems that arise when we have all these new and interesting platforms, like cloud-based platforms or things like data aggregation platforms that we can deploy within our supervision network to get more information from these systems. What dependencies do they create? What are the challenges that they raise? And how do we actually measure whether the risk outweighs the benefit that we derive from them? The other problem is the expertise gap. So it's a people problem. And we've seen, really great advances in training more cybersecurity professionals. And actually, if you read the latest reports from the likes of ISC Squared and those, the global shortage still sits at millions, of experts needed. But the interesting thing with industrial control systems is that it's a very specialized type of knowledge. So yes, while some of the things like web penetration testing can translate, because often PLCs have embedded web servers in them that are vulnerable, you actually need to know quite a lot about all the different types of devices that exist in these kind of environments, your PLCs, your RTUs, your SCADA platforms, the various architectures that those devices may have, your various different types of protocols which are in use, both legacy and newer ones, and increasingly more like wireless HART. And we don't have enough trained personnel in this area. So as a result, in our lab, we actually run also a learning environment. So the box that you see on the right-hand side of the screen here is something that we built within our team here, which we use to actually train students both within our doctoral training center, where we are training a large number of students in this area. But we also have started a new master's program where we are actually training people to learn how to defend these kind of systems. What are the security problems that exist, and how can they go about building effective countermeasures? And finally, the last thing is, of course, how do you actually manage the complexity in these kind of environments? Because as I said, they are very highly connected, these systems. Increasingly, they have a large number of legacy and vulnerable systems, devices, and software systems within them. So how do you actually manage the complexity? So the complexity comes from the fact that we think that our environment has particular qualities, whether they are confidentiality, integrity, availability, safety, resilience. Okay, and an attacker, if the attacker has direct access to the control system, they can actually compromise those qualities in the first instance. But if the attacker doesn't have direct access to the system, they may have access to a neighboring system. Okay, and we may think that that system provides us with certain qualities and certain properties, but if they can compromise that inherently impacts what the system on the left-hand side can do. So the boundaries are not always clear-cut, especially as we saw with the example of pivoting from a cloud platform onto the critical system, that boundaries increasingly start to bleed into each other. Okay, and then of course you have the challenge that an attacker can interfere with the observation and control of a remote user. So while you may think that your system is operating on the basis of the qualities that you expect to deliver in a remote setting, you may be seeing that those qualities are being delivered, but that may not actually be the case. And there are many examples of where physical systems have been compromised, but the operators at the remote end did not know that something was going wrong until a physical observation of the process by being there on the ground has informed someone that something has gone wrong. But all of this is quite complicated because there is increasingly a large number of things interconnected with each other and these critical systems. And getting assurance about these qualities is hard. Understanding where the boundaries is hard, and ensuring that observation and control remains uninterfered is also very, very hard. So I'm going to stop here. If you are interested in any of this, please feel free to get in touch. It is my email address. My apologies again for being late due to the problems with signing in this morning, and I'm happy to take questions.
Thanks, Professor Rashid. It was a very interesting talk. I really liked the idea of control systems in the IoT devices, their role, and the ports you discussed. Now I have a few questions we have received and the registration, and we have also received some live questions. So I will go through it. I will read it out for you. Maybe those questions, we don't have much time, but I will take only a few questions that we think are relevant. Some questions have already been answered in your talk, so I will skip those ones. So my first question is, we have received is, will a PERA or Purdue model will remain the most used, especially with IR 4.0? Is the question.
So, I mean, I think the Purdue model is I think it's unlikely to go away, given that it's quite well known in this domain, and people use it as a way of describing how the systems at a higher level look. But the reality is that the Purdue model has this kind of very nice separation between all these things, and that separation doesn't necessarily exist. So I think if you think of it as a way of just describing what the system at a high level looks like, it's okay. If it is seen as really as a way to, this is what the reality of the system is, then no. But I mean, I think we're likely to see it continue to be used for some time, but that doesn't mean that it gives us the actual reality of what's happening in terms of connectivity in the system.
Right, thanks. So yeah. So the second question we received from in the registration is, it says, can AI and machine learning detect and prevent cyber attacks faster than the humans?
I think that's a really interesting question, and AI is, of course, the kind of often seen as the panacea to solve all security problems at the moment. I think there are two answers to that. I think there is really potential for AI techniques to help in various places. There is a particular value potentially with cyber physical systems like this one, because they can often have very predictable patterns. And if we can train suitable AI techniques to detect those patterns with a high degree of accuracy, then the anomalies become easier to identify. However, there is a catch there, okay? Because if you know how these kind of environments work, then the challenge, of course, is that they often operate within a threshold, okay? Because these are physical processes, okay? You don't always have this kind of very hard separation that you've got this thing. So when the physical process works, the actuator opens, it kind of starts to fill the water tank and so on. And when you close it, there is often this kind of, because of the physical properties of the valve, you can have some leeway into whether it closes in enough time and what is the water level and so on and so forth. So things always work within a threshold. You don't have a hard thing. You always have a threshold in which you think there is safe operation in that regard. So if an attacker can actually operate within that threshold, then that means that they can remain hidden for quite a long time, and even your AI-based anomaly detection system may not necessarily spot them. The other thing to bear in mind is that, of course, AI systems, like any systems, have their limitations. They have a degree of precision and recall that is possible. So what happens for the attacks that they can't potentially detect? But also there are attacks against AI itself. Okay, so if an attacker can potentially compromise what the AI is trying to look for, then you may think that your system is secure, but in practice, it is basically not detecting anything in this regard. So it has potential, but I think when we go to any of such things, we have to think about what are the potential consequences, and not think of it as that it's the silver bullet that is going to solve all our problems. It is a good tool in a range of other things that we need to do. We need to have, better protocol stacks. We need to have more systematic ways of actually gaining assurance across a whole connectivity chain and those kind of things, and so on.
Yeah, one more question, which is very much interesting, and I think I will take it as a priority. It says, in your opinion, what is the biggest misconception when it comes to critical infrastructure security? So he's asking about what is the misconception about security. Please.
That's a really interesting question. I think perhaps the biggest can be that your system is not connected to other systems, because often operators of a system think that their system is not connected to other environments, when through a range of different kind of software platforms, or for example, simply because of business needs, they can be connected. There is many kind of anecdotal stories that I've heard about this over the years, none that I would mention in a recorded conversation, but there are many examples of this where people thought their system was not connected to the internet and discovered that it was actually connected to other systems through some intricate things, intricate connectivity links, for example, through a third-party supplier or things like that. So I think that's the biggest misconception, that people think their system is air-gapped when it's not.
Right, and also we have received some questions. People are confused. They're asking for the difference between IoT and industrial IoT. So they're asking, what is the major difference between both classes, IoT and industrial IoTs?
So, I mean, I think there are many definitions out there of what is industrial IoT, and my definition is probably not going to tally with those other definitions necessarily. But I think if you think about IoT, it's anything in a kind of connected environment, things that you may put in your homes like smart plugs and things like that. But industrial IoT is specifically geared towards the kind of industrial processes that we are talking here, where it can interface with specific types of industrial protocols and industrial environments. It has its own sets of protocols, such as kind of wireless HART devices, which can be placed in these kind of environments. But for example, some industrial IoT definitions also refer to platforms such as Kepware and ThingWorx, where they effectively IoTify your traditional control system components like your PLCs and so on, and they're actually able to pull data from those, as well as from the newer types of sensors that run on things like wireless HART. They could be temperature sensors and things like that, which can all be integrated into a single place. So there isn't a single definition of industrial IoT, but I would say that the key distinction, in my view, is that these are things that are specifically geared towards these kind of environments, which are more hardwaring. They relate to particular properties of these kind of environments in themselves, but also the ability to integrate information from not just the kind of newer devices, but also the older systems into a single space, and be able to do analytics over it. But you're right, the boundary is increasingly blurred, because you may have your kind of regular IoT like smart plugs and those kind of things also sitting in these kind of environments. So perhaps we should stop making this sharp distinction.
Right, thanks. The other question about, again, it's about IoT and industrial IoT. You mentioned in the slide that they're using different like Wi-Fi and other protocols. So he is asking, is there any specific reason why we use Wi-Fi for IoT and why other protocols for industrial IoT? Is there any reason, or we are free to use any one we want?
No, I mean, they often tend to be depending on what you need to do in that regard. So if you, for example, think about Wi-Fi 802.11 has its own properties and it's suitable for particular types of settings. But for example, LoRa in itself is a kind of wide area network protocol. So depending on what you are trying to do, you can't, for example, use Wi-Fi where you need LoRa because you need a wide area network in the first instance. And based on that, because you're communicating using a physical medium, which is over the air, you will need different properties for that communication. So for example, you can have kind of very high bandwidth, but you then can't have potentially very wide reach, or you can have lower bandwidth but a much wider reach. And if you want to look to be able to prove, for example, particular properties, round trip and those kind of things. So depending on where you are, you may need different kinds of protocols in that regard. So that's why you end up with things like LoRa and wireless HART in the more kind of industrial environments. There are other protocols like, for example, Zigbee, but they work on a kind of a ring of trust kind of model. So once you're in there, then you can communicate with everything else, and that may not be suitable because you want to be able to you want to have devices prove particular properties about themselves and not just work on the basis of a kind of this ring of trust kind of model. So there is lots of different reasons you would use different protocols, but Wi-Fi is not necessarily feasible in a lot of the kind of industrial environments where you would have a lot more interference in your environment than you would see in a kind of more traditional setting.
Right. Another question, I think it came from a student who seems interested in the hacking. So he's asking, is it easy to hack or access the industrial control system, or it's easy to hack the data which is stored in the clouds? Because I think he's asking that all the IoT devices, they will send data to the cloud. So is it good to attack the cloud, read the data, and maybe do whatever we want, or it's good to just attack the IoT devices, maybe some control system can be, you can understand the rest.
Yeah, so I mean, I would say that it's not about sort of where do you attack. It depends what your goal is as an attacker, right? And what your goal is as a defender, what is that you're trying to protect. So of course, the data is of great value, and you want to be able to protect the data and information because the information about your processes and their performance and their throughput and their output could be highly sensitive in this regard. But that is only one element, okay? And when we typically think of enterprise systems, we think about data and the confidentiality, integrity, availability. But in terms of industrial control systems, you also have to think about other properties. So the attacker's goal may not at all be data. The attacker's goal may be compromise of the physical process, causing a disruption to the physical process. The attacker's goal might be to impact outage. In this case, impact a large population that cannot, for example, receive power. The attacker's goal might be to compromise the integrity of the process in the sense that if you can't trust that the water supply that is coming into your home is treated and is safe to drink, Okay, that creates a huge problem. And none of that has got anything to do necessarily with the data. It's all to do with the integrity of the process. It's got to do with the availability in terms of the running of the process. And it's also it's also about trust in the end. So, you know, if you can't trust what's coming your way in the end as a population, it creates all sorts of issues. So the attacker may have many different goals. And if the attacker's goal is data, then getting at the data is the goal, and perhaps, you know, going towards where the data is being aggregated, or just remaining within the system. So, you know, there are examples of where attackers have compromised manufacturing processes as a way to actually extract IPR about new types of manufacturing mechanisms or types of materials that are being manufactured. Okay, you don't have to, you know, try just look at the cloud. You can actually observe the process and learn from that. But equally, the attacker's goal might be just, you know, disruption of the process or compromising the integrity of what the process is doing. So one example that I gave you is we started to look at, for example, agricultural processes, and you know, you can think of that if you can disrupt an agricultural process, you can potentially impact the food supply to a large part of the population. If you can compromise the integrity of some of the treatment that food process is providing to the food to make it safe, again, you can have a large impact on a population. So that's an entirely different goal than simply data.
Thanks, Awais. I know its time is up, but I have received so many questions and they are so interesting that I would like maybe the last one questions.
Happy to take another one, yes.
Thank you. So he's asking, is the practice of separating IT and OT a lost case? What would industrial control system security look like a decade from now? So it's a very interesting question. Please, what's your take on it?
I mean, I think we have to accept that increasingly these systems are going to be connected across to each other. And I think it's not a lost cause in the sense that there are good business drivers to do this, right? So the goal has to be that we have to think about what are the architectures that we need to use, security architectures in this regard, so that we can actually get the benefits that we are aiming to get by this connectivity, but without compromising security properties. Now, that is easier said than done, though, because I said at the very beginning that one of the big goals in these systems tends to be around safety, real-time properties, and those kind of things. So your simplest answer to that would maybe, well, let's go put loads and loads of nice authentication mechanisms on this, or, for example, heavyweight cryptographic mechanisms and things like that into the protocols. But the reality is that you won't be able to do that, because you won't then be able to prove the real-time properties that you want to prove about these systems. You won't be able to get the safety assurances that you want the system to provide in the first instance. So I think we need to ask ourselves the question, what kind of security architectures that would work in this kind of setting, but also their interplay with other properties like safety, reliability, real time. And from there, really interesting things will emerge. That is the big research question in this area in the first instance. And I think then you've got other challenges coming your way. So there is increasing talk of, for example, having SCADA in the cloud. Okay, so if you've got SCADA in the cloud, it poses its own challenges, and what are the implications of doing that is not very clear. People are talking about using software-defined networking in these kind of environments, and it can provide interesting ways to manage the networking infrastructure. But what kind of security challenges does it bring with it? That is also a bit of an unknown. So I think the world is changing, and we need to accept that the world is going to change around this. As security researchers, our responsibility is to ask the question, how do we actually do security in this changing world? And what are the kind of fundamental architectures that we can provide that can help with that? But that's a big open question.
So Awais, one more question. It's coming again from the students. They say, we're motivated with your talk today. We want to make it as a career in our industrial control system, like they want jobs in this area. So they're asking, is there any certification or anything we can do to have good jobs in this area?
I think the challenge is that I'm not aware of professional certification, and I wouldn't really suggest a particular one. I think that's the big issue, because there isn't enough trained personnel in this space. I'm not aware of particular things. I mean, the only thing I can say is that I'm aware that we have just started a master's course, and I'm not aware of many others that are out there. So I think the key would be to go and join a good program where you can learn more about this and learn more about hands-on things. And this is not me trying to say, well, come to the Bristol Master's Program. Of course, if you're interested, please do. If you've already got a master's, you may want to do a PhD, but go somewhere where actually people are training people for these kind of things. And there are a few places around the world that do this. There is also a very interesting lab in Singapore as well, and so on. So I think there is no substitute for being able to work hands-on on these kind of systems, to learn the intricacies and to really learn what the challenges are and how do you actually go about doing security in these kind of environments. Without that kind of hands-on experience, things are always going to remain a little bit abstract. So you can learn a lot of these things theoretically, but unless you actually do these hands-on practically, you won't be able to really become the expert that you want to become. But this is becoming increasingly a topic that is, at the forefront. We see more and more research papers on this topic. We see more and more interest in people wanting to work on this topic. But also from an industry perspective, there is a need, but there aren't enough people. So at the moment, the issue tends to be is what is known as, robbing Peter to pay Paul. So, basically industry just sort of, pulls people from other industry organizations, and there remains a kind of limited pool. So there are jobs, but, I would suggest to go and train somewhere where actually people know how to do security analysis of these kind of systems and how to defend against attacks in these kind of systems, because that will give you an advantage in that regard.
Thanks, Professor Awais, for a very interesting talk and the Q&A session. We would love to hear more, but due to time constraints, we are going to end this meeting. So as usual, now I will request my dean to kindly thank the chair and conclude this session, please.
Yes, thanks a lot, Professor Nasr Mallah, for moderating this session. On behalf of Saudi Aramco Cybersecurity Chair, I would like to thank Professor Awais for sharing his great knowledge and sharing his experience today and very important topics related to cybersecurity for industrial control system. I believe he highlighted very important challenges, managing the complexity, managing the weakest link in the system where the attacker can take down the system. I would like to thank also the audience for their engagement, their interaction. I believe they added also very great value to the today lecture series. Looking forward to work with you, Dr. Awais. I believe your lab have very important brief experience related to the chair focus. And I believe we have a lot of common, let's say, projects that could be done in the future. So looking forward to work with you. And thanks again. I believe you joining us today, added a great value to the lecture series, and really appreciate it. Thanks. Thank you.
Thank you very much again for inviting me and having me here, and for all the really interesting questions. Thank you very much.
Thanks a lot.